Okay, let me derive the formula for the energy stored in a spring. We're going to use the same idea. Work is going to be force times distance, right? And if I take a spring and I say I stretch it, right? The work that I do in stretching that spring will be the energy stored in that spring. That's what we always do when we calculate or derive energy formulas. But here we've got a problem because the force, this force here, is changing. If we make a graph of, because this force is equal to kx, right? So it starts off at 0 and it goes up, up, up like that in a straight line. The problem is that the force keeps changing. At the beginning it's nothing, and at the end it's k times x, right? Okay. And so what we do is we say, okay, gee, the average of 0 and kx is 1/2 kx. And we use just the average force. And you can do that with a straight line, right? Okay, so that's 1/2 kx is our force, and then our distance is, of course, we've stretched it x, like that. And we end up with 1/2 kx squared, right? An intriguing second way to calculate this, and here's, that's what it looks like if you can't read my handwriting, right? This is the potential energy stored in the spring, is 1/2 kx squared. K is the spring constant in newtons per meter, and then that's the amount of stretch or compression in meters, right? So if I've got a 30 Newton per meter spring and I compress it, say 15 centimeters, right? The amount of energy is 1/2 times 30 newtons per meter, right, times 0.15 meters squared. Now notice the units are going to be newtons divided by meters times meters squared, which is going to be Newton meters. That's joules, right? So 0.5 times 30 times 0.15 squared. Don't forget to square the x. That's what everybody forgets, right? Is not very many joules, right? That's 0.3375 joules. And then we only have 2 sig figs, so I guess we have to say 0.34 joules. Okay. An intriguing second way to calculate this or derive this thing is to just use a geometric formula, right? The area under here, right? Area is actually the work done. So if you have a varying force, all you have to do is calculate the area under this force versus distance graph, right? And so this thing here, the formula for the area of a triangle is 1/2 base times height, right? And that equals also the work, okay? And the base here is going to be x, right? And the height is kx. And so the area is 1/2 base, which is x, times kx. And again, we get 1/2 kx squared for our area under, which is also the work we did, which is also the potential energy stored in the spring. And that's all you got to know.